Okay, hi everyone. So it's a pleasure to introduce Enrico Garaldi, who I met at MPA, where we were both postdocs. The fun times before COVID happened. So before that, he was a student here in physics. Then he went to Bonn for his PhD. Then came to MPA, and then moved to Trieste at IFPU or IFPU, depending how you pronounce it. And he's moving to Tokyo in January as an assistant professor. So he will talk about the first years of the university.
Yeah, thank you very much. Let me start my timer. Okay, thanks a lot to all of you for being here. Give me the chance to summarize a bit in the, let's say, what I did mostly during the last 4 years or so. So most of my postdoc time, and as you can see from the title, this has to deal with trying to understand better the first billion years of the universe. So this is the epoch of cosmic reionization, and if these words, yeah, okay, and you can see everything all right. Okay, you can see here like a brief history of the universe from the Big Bang all the way to redshift to today. Of course, very biased toward the high redshift universe, I would say. Yeah, my research focus, or at least the thing I want to talk about today, mainly focus on this part here. So when the universe, as we know from the fact that we see the cosmic microwave background became neutral, the hydrogen and the helium in the universe became neutral roughly at redshift 1100 or so. And after that, there is a period of dark ages where we think not much happened. There was no sources of light in the universe, and the only thing that was happening was matter collapsing under its own gravity until the first stars and then first galaxies light up. Let's say redshift 30 or so. We actually were not very sure about it, but we're starting now to see the first galaxies. We have now spectroscopic confirmation of galaxies up to redshift 14. And so we can say confidently that at redshift 14 or so we have the first galaxies in the universe, producing a lot of ionizing photons from the young stars in these galaxies, and these photons start to carve out ionized regions around in the intergalactic medium around these galaxies, and by redshift 6 or so we have completed what we call the epoch of reionization. After that, there is just 90-odd% of the history of the universe until we reach today, where we see that if you look around us, the universe, the intergalactic medium in the universe is fully ionized. The neutral fraction is 10 to the minus 5 or so. And so, as I was saying, this gives us a kind of a first definition of reionization, something that happened between recombination and today, that somehow ionized the intergalactic medium. And as I already told you, we think now this occurred around, let's say, 15 to 6. And I just wanted to point out that, in fact, there are two epochs of reionization. What everyone talks about when it says reionization is this one that I just described, when hydrogen is ionized. For helium to be doubly ionized, we need to wait a few more billion years, around redshift 3.5, I would say. Helium reionization occurred, and we think this was driven by quasars. But today, I'm not going to focus on helium reionization at all. So whenever I say cosmic reionization, I will this means hydrogen. So what we know about reionization changed a lot in the last decade or so, and even more so in the last few years with the launch of JWST. So this plot shows you the volume average neutral fraction of hydrogen in the universe as a function of redshift. And if I were to show you this plot a few years ago, basically you would have just a couple of points above redshift, 7.5 or so. Well, today we are starting to fill up this plot. And the three curves that you see in the background are three different models that have different sources, so different galaxies that are powering the reionization of the universe. I will not go into the details. That's not really, doesn't really matter for today's talk. What I just want to point out is that we are really starting to be able to tell apart different models for the reionization of the universe, which is definitely not something I could have said 2 years ago. So we know we were pretty confident that ionization ended by redshift 6 or to 5.5. And what we also are pretty confident about is that this was driven by galaxies. There is some small corner of the parameter space where quasar could in fact do the job, but I would say the overwhelming majority of evidence is in favor of galaxies. What we actually done, so you can see this here. This is from a simulation. You get the on the vertical axis the H1 photoionization rate. So how many ionizing photons you have in the universe per unit time, unit volume, as a function of redshift. And you can see the total is the blue line. The contribution from galaxies is the dashed orange line, and the contribution from AGN and quasar is the green line. So at redshift 6 to 7, the bulk of reionization, when the bulk of reionization happen, there are 2 orders of magnitude at least of difference in these 2 curves. So 99% of the photons at least are produced by galaxies. What we actually are not particularly sure about is which galaxies were driving ionization. The consensus right now is that the small star-forming galaxies are producing the bulk of ionizing photons. These are conveniently outside of what we can actually see with telescopes, and so we actually don't observe the bulk of the population that we think drove ionization. But different work find different, typical masses for the galaxies ionizing. What is also remarkable, and has changed a lot in the last couple of years, thanks to JWST, is that we are starting to observe these galaxies in the epoch of ionization. I just realized my Zoom thingy is covering the titles. Let me see if I can move it. Yeah, excellent. Yeah, we're starting to characterize the first galaxies in the universe, from the sizes to the metallicity and UV slopes. But the more we observe these galaxies, the more questions we find. And I've tried here to summarize some of the main questions. I'm sure I missed out your favorite one. But first of all, let's start from the fact that we actually observe galaxies at redshift 14, and these are spectroscopically confirmed, and these are very bright, and something that we would not naively expect from our models. And then if you just take these and have to do some extrapolation because we don't see the full population, but then if you believe this observation and your extrapolation, you conclude that there are too many photons for ionization, meaning that ionization should have been completed by redshift 10 or so, while we know that's not the case. And so one should ask why, what are we getting wrong here? Extreme emission lines in galaxies. This is something that was quite unexpected from one of the first results from JWST. The fact that we find all stellar population just as in few tens of million years, just a few 100 million years after the Big Bang, and then maybe also these 3 galaxies up to redshift 6. So there is we are essentially discovering a new part of the universe, we're observing for the first time this period, and this is giving us more questions than answers, which I think is good, especially because the situation is now this. We have a few instruments that allow us to peer all the way to redshift 6 and above. I mean, there are of course more, but these are some of the main ones, and the reason why there's not more is because I need space, because in the next 10 years or so, a huge number of instruments will have the first billion years of the universe as one of their key science goals. So of course, JWST already spoke a lot about it, but the intensity mapping, line intensity mapping experiment like Concerto, FYST, SphereX, these all are targeting the high redshift universe, let's say the first billion years or 1.5 billion years as part of their science goal. We have the ELT, of course, will allow us to see the metal forest all the way to redshift 8. And so this is, I think, a unique time to really try to study the high redshift universe. But also, this will enable something that we are not, that we cannot do right now, which is not only study, say, galaxies or the intergalactic medium, but also their connection, how these 2 processes talk to each other and influence each other. So one of the hard things to do, though, is to bring the models, in particular simulation, this is my area of expertise, to the same quality of the observation that we get. And what I mean by this is that models were developed, of course, to explain the observation we had. And so these were typically low redshift observation in the low redshift universe. And so they made typically a number of approximations that work very well in the local universe, but do not work anymore when we talk about the first billion year of the universe. So just as a brief recap, the simulation works like this. I'm sure you all are familiar, well, know this. You have some machinery, which is your simulation code, where you try to put all the astrophysics or you can afford to simulate, and then feed in two ingredients, right? What you think is the content of the universe, and what you think are the initial conditions for the evolution of the universe. And this, if you do your job well, this will spit out a realistic universe that you can then use to run your experiment and compare with observations. So typical ingredients of simulations are gravity, hydrodynamics, radiation, magnetic fields, and so on. Some of these, and depending on the simulation, you might be able to resolve, like self-consistently solve for few of these, say gravity, hydrodynamics, and maybe not resolve the other, say star formation, and so you put it in via a so-called subgrid prescription. I bring this up because the first billion years of the universe is unique in the sense that if you are concerned about the post-reionization universe, you can essentially ignore radiation. This is a very good approximation from redshift 5 on. But if you want to study what happens before that, when the radiation field is very inhomogeneous, well, it's a pain. So the main reason why it's a pain is the following. Well, why it's important, sorry, is the following. What you see here is the evolution from redshift 20 to 6 of the photon density in 100 megaparsec cubic volume. And you can see this is extremely inhomogeneous. So if you want to really capture how this region here differs from that one, so the one that is ionized and heated up differs from the next one that has not been ionized yet, you need to follow radiation. But radiation is very expensive to simulate, simply because it moves very fast. And so if you just naively take a normal simulation, hydrodynamical simulation, and you switch on the radiation transport, it typically gets 100 to 1,000 times more expensive. If you are below redshift 5, you can just ignore that and assume there is a uniform, spatially homogeneous UV background, and this makes your simulation much cheaper. Unfortunately, radiation is important, especially throughout the entire history of the universe, but I would argue even more so in the first billion years. For example, it modulates the gas accretion onto satellites and can suppress up to 70% of the gas, 40% of the gas fraction accreted by satellite galaxies. It can impact really strongly the CGM conditions. So if you are interested in a circumgalactic medium and you forget about radiation, you can get the H1 column density wrong by 6 orders of magnitude or so. And then it can also change the dynamics of satellite density. It changes what stars form and so how resilient they are to tidal stream. The problem is that even once you include radiation, the way to having realistic simulation that you can trust and compare with observations, it's full of birds or monsters, as I put here. And so during the rest of my talk, I've accurately selected these three because these are the one I've worked on. So during the course of the talk, we will tackle each one of these. Well, I'll show you how I try to tackle each one of these. So let's start from this one down here. The first step of my talk will be talking about a simulation project called TISAN, which tries to solve the disconnection between high and low redshift. What I mean by this is that for the reasons I already told you, it's pretty clear that I think simulation of the low redshift universe and the high redshift universe are different. Tend to use somewhat different techniques and having different ingredients. One problem, I think, is that these are not connected, because if you're interested in the low redshift universe, you're missing ingredients that you need in the high redshift one. And if you're looking at the high redshift universe, typically you don't have the time to run all the way to redshift 0 because your simulation is just too expensive, so you stop at redshift 6 or so. But this is as issue. So in this paper a few years ago was pointed out that if you take one of these models that's working very well in the high redshift universe and try to push it just to redshift 4 instead of 6, your galaxies start to look strange. They are bulge dominated, the rotation curve is completely strange. It's just the model was not ready to go past redshift 6. So what did we do to try to fix this? The idea is what then eventually became this Tizen project that we published 2 years ago now, is to take models that were calibrated to low redshift, supplement the physics that is missing for the high redshift universe, and then try to see how this works. So we take the illustrious TNG galaxy information model, a very successful galaxy information model indeed. We supplement cosmic dust physics, radiation transport, and because we just take them and do not modify anything from this model, we essentially are left with a single field parameter that we can tweak at high redshift, which is the escape fraction of photons from the birth cloud of star that we loosely tweak to get the right reionization history. And then, because we are not sure about what's going on in the high redshift universe, we include a number of physical and numerical variations. So essentially, we change which galaxies are driving the reionization of the universe. Are they small galaxies? Are they the biggest one? And also the dark matter model. Although I must say this is a kind of an extreme model. Is this a strong dark acoustic oscillation model, which is essentially a proof of concept to see the maximum amount of impact we can expect dark matter to have on reionization properties. And the key feature is that we have a large boxes, so we can actually capture statistically the progress of reionization. Typically, you need 100 moving megaparsecs or above in volume to capture these. And also, we restore the atomic cooling rates. We think are the smallest halos that significantly contribute to the reionization thing. And so if you compare these to other similar radiation-hydrodynamical simulation, so you see here the simulated volume on the x-axis versus the force resolution, Tizen is here. So we are here at on the right-hand side where we start to get converged reionization history. That's what I just told you, 100 megaparsec or above is the requirement. We do not simulate the ISM. We just don't have the resolution. So whatever comes out, all the predictions that come from the simulation are agnostic to the ISM of the galaxy. We just cannot simulate that, right? And this is a choice. You could move up here. You have the resolution to simulate the ISM, but then your volume is tiny and it's not statistically significant. So this is how the simulation looks like. You see the dark matter, gas, and stellar density on top, H1 fraction, H2, so ionized fraction, temperature, and photon density. And this is maybe a video you have seen multiple times. Reionization starting from small bubbles that eventually coalesce and ionize the entire intergalactic medium. What is special, I would say, about this simulation is that because we use the quite advanced numerical techniques, but also a lot of computing time, we can zoom in on a single galaxy and then see all the details of this galaxy. Oh, the bit is a bit choppy, but a single galaxy, magnetic fields, we have dust, especially varying. This is the temperature, and then this will zoom in again to show you the details that we can get for galaxies in things. So we can get this level of details. We don't get the full ISM, of course, I just told you why, but we still kind of can see the galaxy structure and quite some details about the galaxy. So the last thing I want to say before jumping to the results is that these data are all public. Essentially data products we ever created from this simulation, from all the papers related to the simulation is public. And in case any of you is interested in using them, just write me an email. There's merger trees, there's mock images from JWST, there's a cosmic web, so filaments, and anything well, not anything you would like, but many things are there. And then we have tested thoroughly that this does not only create nice images, but also captures the properties of the universe. So I divided this in 3 groups. I will not go through all these plots, don't worry. But essentially, what this should, I hope, delivers to you is that we are doing a good job at capturing galaxy properties, so ionizing escape, UV luminosity functions, properties of intergalactic medium, say the mean free path of ionizing photons or the optical depth of the intergalactic medium, and also some JWST observations that came out after the simulation was run. So the simulation could not have been calibrated to get these observations, and yet we get a decent agreement with them. So I think this also shows what I think is unique about this set of simulations. So that keeps together the galaxy formation, the properties of galaxies on a population level, and the intergalactic medium properties. And so that's why what I want to focus a bit is on the galaxy-IGM connection. And there are many ways to study this. We could look at the bubble size, ionized bubble sizes as a function of galaxy property. You could look at the escape of radiation from galaxies and how it propagates in the IGM. What I will focus on is a probe that tries to probe how a galaxy that is here at the center and the ionized bubble, so this yellow circle here, affects the intergalactic medium around it. So this is a schematic view of all the processes, the complicated things that go on in a galaxy, you know, accretion of crystalline gas, reprocessing, creating ionized bubble, and spend some time describing this to you. And then if you take a background quasar and that passes somewhat close to the galaxy, you can look at the Lyman alpha forest of this quasar and see if it is affected by the galaxy. So what do I mean more precisely? So the Lyman alpha forest, as you are familiar with, is a very sensitive line. So essentially, it's typically the brightest line in quasar spectrum. And while this light travels towards us, it gets absorbed by neutral hydrogen along the line of sight. And what is creating these features that we call the Lyman alpha forest. Now there are 2 things I should say more about this. The first one is that the Lyman alpha cross-section is very large, which means that just a ionized neutron fraction of 10 to the minus 4 would completely absorb the incoming flux. This means that Lyman alpha can be completely absorbed even if if the universe is actually ionized, right? And the second thing is that because of this, there is typically no flux left at redshift greater than 6. So if you look at a quasar at redshift greater than 6, you typically see, the continuum all the way to the Lyman alpha, and then what is called the Gunn-Peterson trough here. So this is the continuum, Lyman alpha, Gunn-Peterson trough. Everything is absorbed because the universe is just not sufficiently ionized yet. But then if we use high-resolution spectroscopy, we can actually start to see that there is some tiny regions where there is flux transmitted in the Lyman alpha, in the Gunn-Peterson trough. And this, I'll skip a bit, so ask me later if you're interested, but essentially this traces the first highly ionized bubbles around galaxies. You can go into simulation, check that this is indeed what happens. And so then one can imagine that if you take your galaxy and look at the quasar passing next to it, you would expect the Lyman alpha forest here in this part where it goes close to the galaxy to be different from the Lyman alpha forest in neutral regions of the universe, right? And you do this statistically, so you put together as many line of sight as you can, and then you get something like these yellow points. And indeed, these were recently updated with some better observations. So, you get something like this. So in these regions, very close to where the distance between the galaxy and the line of sight is small, you get that the Lyman alpha is suppressed. So what I'm plotting here on the vertical axis is the transmissivity, so how much flux you get in the Lyman alpha, divided by the average in the universe -1. So this line here shows you the average Lyman alpha flux in the universe, essentially. So if you have a suppression here, and it's easy to understand, you are getting very close to the galaxy, so you are probing an overdense region of the universe. Overdensity means that your recombination rate of free protons and electrons is very high. So the neutron fraction is typically, let's say, larger than 10 to the -4. That's enough to completely absorb your Lyman alpha. when you're very far from it, this you see goes back to the average. And again, the reason is that you're simply probing a random region of the universe. At that point, the presence of a galaxy here does not matter anymore for part of the IGM, which is very far from it. And so you just statistically recover the average in the universe. And then there is this interesting feature here where there is an excess of transmitted flux at intermediate scale. And this, we think, is really probing the ionized bubble around the galaxy up to the scale where the overdensity where the galaxy lives takes over, right? So the ionizing radiation here boosts your flux. The overdensity here suppresses it, and so you get this typical shape. If you accept this interpretation, which by the way, you can just explicitly check in simulation. This is a stack. You see that the UV photon density extends to much larger distances than the gas density. Then you can go into simulation and try to see if your simulation is able to capture this. And what I'm showing here is a very interesting, well, for me, very interesting plot, because it shows two simulations. One is this Tisan simulation I just described to you, and another one is CROP. And these are two simulations that are excellent at reproducing most of the, if not all, the intergalactic medium properties during reionization. But the moment you try to fold in this connection to the galaxies, you see that Tisan manages to capture this modulation while CROP just fails. And the reason is that CROP was not built essentially to reproduce the galaxies, but just the intergalactic medium property. So I think this is an example of how connecting these two somewhat typically distinct areas of research can really improve constraints on your models, say. Not only that, you can use your simulation and predict that these changes, the signal here changes a lot with reionization, with ionized fraction, so from the beginning to the end of the reionization. And so if that's true, you can use this to time, for example, reionization. So this has actually been done 2 years ago by Daichi Kashino and collaborator from the Eiger survey. They find this signal. Let's look at the blue line, and that they compare with indeed Tisan itself and conclude, that the reionization should occur a bit earlier than we thought. But the problem with this study is that they have a single line of sight, and with a single line of sight, you can see here the noise is too large. What I mean is the following: for each of these panels, I show you the signal, this signal here, so the cross correlation between Lyman alpha and galaxies. For individual line of sight here in blue, for 10 line of sight together in purple, and for 25 in orange. And so this dashed line is the same as that at the blue line here, and you can see that is within the statistical noise, the fact that each line of sight probes a different part of the universe, which has unique peculiarities in how the structure formation process goes on there. So you need between 10 and 20, I would say, lines of sight to probe and factor out the intrinsic variability of structure formation. And luckily, both the Eiger team and the Aspire team are collecting this, and I think by the end of the year, we should have around 35 or so lines of sight. I know they already have the data, they are analyzing them. So we might be able to have a first measurement. Okay, let's move on. This is something, done. We have, I think, a good stepping stone to improve what we know about the hierarchy of universe, but there are still two of these obstacles. And the first one is not really peculiar to the hierarchy of universe, is the fact that whenever you run a simulation, you have to choose whether you want to cover a large volume or capture the details of, say, galaxies in this case. And again, as I said before, this is made worse by the fact that radiation transport is so expensive. So this is a good example, I think. Same plot as before. We would like to be up here, because JWST, this is what JWST is seeing, right? The real universe has surely a converged reionization history and infinite resolution. And then this and the simulation I showed you before gives you something like this level of details, and then you could go to another simulation that has a much smaller volume but higher resolution, and you see that the level of details again is much larger. But then you lose the statistical power because the volume covered by this Sphinx simulation is so tiny compared to what you would like to even just have converged reionization history. So the way I decided together with my collaborator to deal with this is to take this Thyssen simulation we have and then zoom in on individual galaxies inside it. And so far, nothing groundbreaking. What is special, I would say, is that for this Thyssen run, we recorded very high time cadence, the radiation field, which means that the typical issue you have in zoom-in simulation of the reionization epoch, which is you focus your entire computational time on a small patch of the universe, but you need the large-scale effect. And if, with gravity, we have a solution, you just have low resolution outside and you still capture the long-range gravitational interaction. When you are looking at the reionization epoch, you have the same issue for radiation. And so how do you get radiation from far away in a realistic manner? But because we have this high time cadence recording of the radiation field, we can just inject the radiation field outside of the high density region. So this is now from the simulation itself. The white boundary here shows you the high density in high resolution, sorry, inside and low resolution outside. And we are injecting the correct ionization field outside, and this just propagates in, and in this case, ionizes this tiny galaxy there, which is the one we are focusing. So I think, as far as I know, this is the first time this has been done in high redshift simulation, where you have not only the gravity from the large scales, but also the radiation field. And this allows us to get something like this. This is a test run. So essentially isolated galaxy plus external radiation field, but we get very high resolution and somewhat realistic looking galaxies, let's say, although we don't really have an idea of what is how a galaxy trajectory 10 or so looks. So this is still ongoing. Hopefully by the end of the year, this will be published, but yeah, I've said this many times. But yeah, here we have a multi-phase ISM model, so we capture the physics of the interstellar media that we were not capturing in Thyssen, and that's because we can zoom in very much. We have improved a bunch of physics, including the dust. So you can see here, if you look at the color point, how they follow models and observation, while the old Thyssen, which is this empty contour here, was failing miserably. We follow the dust temperature. We have correction for H2 regions that are unresolved, and then all these with a high resolution, up to 100 solar masses resolution, so we can make prediction for all the emission lines in high redshift galaxies. For now, I will not say more about this. We just finished the simulation. We are analyzing the data. I don't have many results yet, so I'll just talk about something else soon. I just want to point out that if you put this here and you have faith in how you inject the radiation field, so you can trust your large scale structure as well as the small scale structure, you would get something up here, very far from any other simulation on the market. Of course, at the price that we only resolve few galaxies in this way, so we have around 20 galaxies, and not a full box. So this is not, this is not a proper comparison, but at least for some galaxies we sit up. Okay, another way we have tested to tackle the fact that simulations, especially radiation hydro, are necessarily limited in volume, is to find tricks to improve their statistical faithfulness. So this is a work by Anshuman Acharya, who is on the job market. So in case you are looking for a very good student that essentially has done everything from stellar physics to radiation hydro simulation, look out for him. What we did was to take this paired and fixed approach. Essentially, it's a statistical, I would say, it's a way to produce your initial condition for the simulation in such a way that, if you run two boxes with this paired and fixed approach, so with specific initial conditions, and you average them, the statistical fluctuation that you normally would have just average out to the third order, I think, and so it boils down to the following. When you produce initial conditions for your simulation, you inject a power spectrum that you think is the power spectrum of the universe at the initial condition. And typically for each mode, for each k value, you sample the actual value of the power spectrum you put in the simulation from a Gaussian. And you need to do this to have a Gaussian random field in the initial condition to be a Gaussian random field. But Raoul Angel and Andrew Ponson showed in 2016, I think, that if you can just get rid of this, just take the average value, what you expect. And this will break the assumption of Gaussianity, but will not have any significant impact on your observable, as long as you're not looking for non-Gaussianities. And this is shown here. Essentially, the yellow curves are two of these simulations with this pair and fixed approach. The blue, the points are the average, and the blue line is the average of a few hundred, I think, in individual realization without this approach. And you can see that with just two simulations, you get a level of accuracy which you normally get with 100 simulation runs. So that's great, but this works for things like the power spectrum and statistical measures over the entire universe, right? And the problem with reionization is this is surely a statistical, in some way, you can do statistical measures, but it's also sourced by very local properties of galaxies, which were shown to not gain anything from this paired and fixed approach. And so the question is, can we still gain something if we use this paired and fixed? And so to make a long story short, Anshuman ran a number of radiation hydro simulation, exactly the same setup I described to you before, just smaller, lower resolution, and then compare this with the pair and fixed simulations. And what comes out at the end is the following. So you have the improvement factor. So how better one pair and fixed simulation is compared to two random simulations, so same volume, but one with and one without this pair and fixed. As a function of redshift, because of course reionization evolves a lot. And use two approaches. Ask me later if you are interested, but essentially this tells you that you are around, you have an improvement around a factor of 5 at least, maybe 10 if 5 to 10 in the volume, in the effective volume of your simulation. This means if you use this pair and fixed approach and then compute quantities like the 21 centimeter power spectrum or other statistical quantities, even in the case of reionization, so sourced by local galaxies, you still get the same result as you would get if you were running, say, 10 normal simulations. And the last thing I want to discuss about quickly is numerics versus physics. And what I mean by this is that whenever we run a simulation, we, especially these that are extremely expensive ones, we always need to make a choice. We need to make a choice of, say, a model that we trust more than the other. And so, yeah, here I put some examples. Tizen, the simulation I described to you, only the main run took 39 million CPU hours. If you include the physics variation, we go up to 51. Sphinx, 120 million CPU hours. Coda 3, another simulation of the high-redshift universe, 6 million GPU hours. These are numbers that means essentially that you can run one simulation, two if you're lucky. And so you have to choose a model, choose a parameters, and then trust that this is, the correct description of the universe. And there has been work in the past looking at this, how different codes and models change your prediction. But one thing Aniket, indeed, also on the job market, also very good, it has been looking at is how the supernova feedback in the simulation changes. So not only the supernova feedback, as in, how much energy we put in or things like this, but rather the implementation, the technical implementation of the supernova feedback. So in particular, we took a set of, again, radiation-hydrodynamical simulation, very similar to what I described to you before, and then changed a single thing, which is how we inject the supernova energy. So for now, forget about the model name, but let's say we have a model where we just put all the energy, sorry, all the energy from supernovae, from a stellar population, 10 million years after the stellar population is born, all with the same fixed energy. This is something that is commonly done, I would say, or was commonly done. Then we have a variable injection. So we inject it at a time that depends on the mass of the star that is exploding, but again, fixed supernova energy. And if you put these two together, you get essentially 99.9% of the simulation ever run. And then there is one where you also varies the supernova energy together with time based on the stellar mass, including hypernovae at low metallicity. So these deal with the fact that in the hierarchy of universe, if you really want to follow this, you might get extremely powerful supernovae. Well, very rarely you might get very powerful. And so at least the first two, I would say, if you were to ask me a year ago, I would have told you that they don't really make a big difference, at least for the global properties of the universe. Galaxy properties, maybe yes. But what it finds is that, in fact, they affect a lot of things, starting from the galaxy morphology. So this on each column is the same galaxy, just run with these three different models. So you go from grand design spiral all over the place to completely amorphous galaxies to a mix of the two. This is already quite surprising to me. The reason is that essentially, if you inject all the supernova energy at the same time, this completely, as we do at the top, this completely destroys your disk. But then you are done with the supernova, so the gas can just collapse again, form again a disk, and forget about the fact that there was ever a supernova. While if you keep injecting a supernova here and there for 40 million years, you just never give the time to the gas to settle down onto a disk. And here, of course, is a mix of it. The rotational support, as you can imagine from looking at this, is a very high rotational support, is a non-rotational support, essentially. But also the reionization history of the universe. This shocked me. I thought for a week or two that he just made a mistake in the plot. Because what you see is that if you just take this model where you inject all the energy at the same time, you get this curve here, reionizes more or less at the correct time. But then you put what we think is a more realistic model for supernovae, and you just never reionize. By redshift 5, it's still like 80% neutral in your universe. And we know for a fact from observation that this is wrong. This cannot be the case. Unfortunately, most of the observables we have access to now are not affected. So this is the UV luminosity function. Once you fold in dust attenuation, these are the dashed curves, there is essentially no difference left in the observable range for the UV luminosity function. There is a difference here at redshift 5, but this is just too faint to be observed for now. Star formation dry densities of the universe, this is the same. The galaxy main sequence remains the same, and the ionizing efficiency of galaxies also stays the same. This is quite disappointing because it's hard. This means that it's hard to determine observationally which is the favored model of this. Although I remind you, this model, there is a clear hierarchy, but from the least to the most physically motivated one. And the one that works better for the reionization history is the least physically motivated. So we need to think about why. We have ideas, but we don't know yet. But the picture that emerges from here is that supernova feedback changes the morphology in the way I told you, depending on when you inject the energy. This changes how photons escape. So if you have a disk, photons escape more easily because it's essentially they escape perpendicular to the disk where the density is very low. So it's easy for photons to ionize and then escape. While if you have a very complicated blob of gas, these tend to be absorbed much more easily. And this then changes the reionization. So I think the takeaway message from this is that even details of how you inject the feedback in your galaxies might impact the larger scale in the simulation. And this was very interesting, also very disappointing. It's a headache if you want to run a large scale simulation. And with this, I think I'm done. I haven't checked the time, but hopefully it's not too bad. So yeah, these are 4 steps I took in the past few years to try to get towards a much a higher accuracy in simulation of the universe, and therefore a bit better understanding of what goes on in the first billion years, starting from putting together IGM and galaxy science and study their connection, to techniques to improve at least the effective volume of our simulations without sacrificing too much in resolution, and finally studying the nitty-gritty details of how implementation and algorithm can actually change a lot about your prediction of what is the universe and the hierarchy it is. Thank you.
Okay, questions?
Yeah, thanks a lot. Really nice talk. So I was interested, especially in the first part of your talk.